Hi everyone, so in this video I'm going to talk about AVL trees, which stands for the name of the researchers that came up with it, Adelson, Velsky and Landis. And basically what it is just a binary search tree where we've added in some kind of condition to make sure that the height of the tree remains reasonable. So remember when we spoke about binary search trees, we said that in the worst case, when we're inserting or deleting or searching for something, we have to go through the entire height of the tree. So it's very important that we have trees that look like this on the left rather than those that look like this on the right. So it's very important for us to be able to say that the height of the tree is going to be reasonable. So on the left hand side we see that the height of this tree is going to be logarithmic in some sort. So it's going to be order log n, while on the right hand side we see that it's going to be order n. So the amount of work that we have to do in the worst case in each of these can be quite different. So the AVL tree basically introduces an extra balance condition, and it makes sure that we always get these nice balanced trees that you see on the left rather than these single paths that we see developing on the right. Okay, so what is this balance condition? So it has to do with the height. So if we look at the height of a node, so some node x, right? We say that the height of that node is equal to the maximum height of its two children. So it's the max of the height of the left node or the right node. And it's going to be that plus 1, because we've now added in this extra node. We then said that if the node itself is a leaf, it's going to have a height of 0. So the height of a leaf is equal to 0. But more than that, we're going to add in and say the height of an empty tree, or the height of null, is going to be negative 1. And we do that for convenience, and we'll see that it works out to help us in later on. So the AVL condition then says, take the height of the left node and compare it with the height of the right node. And the difference between them, in absolute terms, must never be more than 1. So the difference between the left and the right must always be 1, 0, or minus 1. And that's the AVL condition, and we'll see that in any tree where that is always the case, then we're guaranteed that the height of that tree will be logarithmic. Okay, so suppose we have a tree that looks like this. We now want to be able to go in and fill in the height of every node. So we're going to be able to say, well, the height of node 3 is going to be 0. The height of node 1 is going to be 0. The height of node 8 is also going to be 0, because these are all leaves. We can say the height of node 4 is going to be 1. The height of node 2 is going to be 2. And the height of node 5 is going to be 3. So the question then is this an AVL tree? So the first thing we can do is we can say, okay, well, let's look at node number 4. Its left child has a height of 0, and we said that the null pointer, we're going to say, has a height of negative 1. So 0 and negative 1 differ by 1, and so we're okay, this node is balanced. When we look at node 1, well, its left child has negative 1, its right child has negative 1, and so that's also balanced. Those are the same. When we look at node number 2, its left child has a height of 0, its right child has a height of 1, and so the difference between them is 1, and so that's okay, that node is balanced. When we look at node number 8, we see that its left child has a height of negative 1, its right child has a height of negative 1, and so those are the same, and so it's balanced. When we look at node number 5, we have a look and we see its left child has a height of 2 and its right child has a height of 0. 2 minus 0 is 2, which is bigger than 1, which means that at this point the AVL condition does not hold. So this tree is not an AVL tree. All right, so let's look at another example. If we look at this one, we can now go through and we can say, okay, what are the heights of all the different nodes? So node number 1 has height 0, 3 has height 0, 7 has height 0, 4 has height 1, 2 has height 2, because it's the maximum of 0 and 1, which is 1, plus 1, which gives us 2. 8 has a height of 1, and 5 has a height of 3 again. Cool. So now we go through and we say, okay, does the balance condition hold? So we have a look and we say, well, node number 1, its left child has a height of minus 1, its right child has a height of minus 1. So we can even draw that in like this, and we can say those each have a height of negative 1. So in that case, node number 1 is balanced. For number 3, we see that each of them have a height of minus 1, and so they're equal, and so it's balanced. For node number 7, we have the same thing, minus 1 and minus 1, and so we can say that node number 7 is also balanced. We then have a look at node number 4. Well, its left child has a height of 0, its right child has a height of minus 1, 0 minus 1 in absolute terms is equal to 1. So we're happy that indeed that one is also balanced. If we have a look at node number 2, we can see that the left child has a height of 0, the right child has a height of 1, so the difference between them is 1, and so that one's also balanced. If we look at node number 8, we see the left child has a height of 0, the right child has a height of minus 1, so the difference between them is 1, and so that's also balanced. Finally, if we look at node number 5, then we see that the left child has a height of 2, the right child has a height of 1, and so the difference between them is 1, and so that is also balanced. So in this case, this is an AVL tree because the AVL property holds throughout the entire tree. It holds for every single node. So I made a claim earlier that said that if the tree satisfies the AVL property, then we're guaranteed that the height of the tree is going to be logarithmic. And we can actually prove the exact height, an upper bound on the exact height of the tree. And so we'll look at this in a bit more detail later on. But for now, if you're happy to just accept that the height is an element of big O log n, and later on in this video, we'll look at actually proving that. So if we think about the different kinds of things that we can do to a tree that will actually change it, we only really have to worry about insertion and deletion. When we're doing things like, does it contain a number, or if we're doing a traversal, we're not actually changing the tree. So we only need to make sure that insertion and deletion maintain the AVL property. That if we insert a number, we make sure that we haven't broken the AVL property, and if we have, we need to fix it. Or if we're deleting a number, we need to do the same thing. Now, we can say that when we insert or delete, we know that we can only break the balance along the path from the node that we've just inserted up to the actual root of the tree. So if I have a tree and I insert a number, I know that I'm not going to break the AVL property on the other side of the tree. I know that I'm only going to break it from where I am up to the root, possibly. So we're going to introduce something called a rotation. And so we see that there are actually going to be 4 different kinds of breakages that we can have. And we're going to have breakages where we have nodes along a straight line like this, or we're going to have breakages where we have some kind of zigzag shape like that. And in those cases, we want to be able to see how can we fix the AVL property. So just to be sure, let's have a look. So the height of this node, maybe let's give them all names. So X, Y, and Z. So the height of the node X has a height 0. Height of node Y is 1. And the height of node Z is 2. And if we look at the balance, we see that the left child of X and the right child of X both have heights of -1. So X is balanced. If we look at Y, we see the left child has a height of 0 and the right child has a height of -1. And so the difference between them is 1, and so Y is balanced. But now if we look at Z, we see that the left child has a height of 1 and the right child has a height of -1. And so the difference between them is 2, which means that at Z, the balance is broken. Similarly, if we look at this shape on the right, we can have X, Y, and Z. And for the exact same reasons, we'll see that the balance doesn't work out. So the left child of X is -1, the right child is -1, and so the difference is 0, and so that one is balanced. For Y, the right child is -1, the left child is 0, so the difference is 1, and that's balanced. But for Z, if we look at the left child, we see 1, the right child we see -1, 1 minus -1 is equal to 2, and so the balance is broken again at Z. So we need to introduce some kind of rotation that is going to allow us to fix these problems. So imagine you have a tree that looks like this, where we have some node X, we have some node Y, and then Y has a left subtree, which we've just called A. It has a right subtree that we've just called B, and it has and X has some right subtree called C. So we know that this is a binary search tree, and so there must be some kind of ordering. So we know that A, everything in A is going to be less than Y. Everything in B is going to be greater than Y, but still less than X. And everything in C is going to be greater than X. So we have this kind of ordering, and we need to make sure that after our rotation, we haven't broken anything. Okay, so when are we going to have a problem in this situation when we at X? So let's say for argument that the height of A is going to be H. That means that the height of B is allowed to be the same, so it could be H. It could be 1 less, H minus 1, or it could be 1 bigger, H plus 1. Right. Now, let's just, for the sake of simplifying the argument, let's say that we choose it so that H is going to be the larger of the two children, the taller of the two children. So in this case, it means that the height of Y is simply going to be the maximum child plus 1. So it's going to be H plus 1, so H plus 1. Then the height of C is going to be either H or H minus 1. Okay? And we said that if we expect there to be a problem, then the problem must be at X. And so we're going to say that the height must be H minus 1, and that would then cause a problem, so that the difference between them is going to be 2. So we need to come up with some kind of rotation that's going to allow us to fix that. And so we see that if we now reroute the tree at Y, so we say, I want the root of this subtree to be Y. We then say, okay, well, where does X go? Well, X is bigger than Y, so it must go to the right. And then where does everything else go? Well, again, we simply say, where are the big and small numbers? So everything in A is less than Y, which means that it must go to the left. Everything in B is bigger than Y, but less than X. So it's bigger than Y, so we go right, but less than X, so we go left. And finally, for C, everything is bigger than X, and X is bigger than Y. So it's bigger than Y, we go right. It's bigger than X, we go right again. All right. So let's have a look at the heights of everything again. So we said that the height of A was H. We said the height of B was either H or H minus 1. And we said that the height of C was H minus 1. So from there we can say, well, the height of X is simply going to be the biggest height of its child plus 1. So the height of X is now going to be H plus 1. While the height of A is simply H. So the height of Y is going to be H plus 2. Let's have a look at the balance. Well, for X, the height is H or H minus 1. The right hand is H minus 1. So the difference between them is either 1 or 0. In both cases, that means that that X is balanced. If we look at Y, well, the left-hand child has a height of H. The right-hand child has a height of H minus 1. And so the difference between the two is just 1. And so that means that Y is also balanced. And so we've seen that by doing the single rotation, we've now managed to fix the AVL property that was broken. And so this happens when we insert on the left and X was already left heavy. So X, the height of the subtree on the left of X was already 1 bigger, and then we inserted and that height went up. And so then we needed to do a right rotation about X. And in the same way that we did a right rotation on X in order to go from this left-hand side to the right-hand side here, if we have the situation on the right, but the heights are broken, then we can say we can do a left rotation on Y, and that would get us back to the original. So suppose that we have this tree, and we would like to insert the number 6. So the first thing we need to do is make sure that this is indeed an AVL tree. So let's have a look. The height of 1 is going to be 0. The height of 3 is going to be 0. The height of 7 is going to be 0. The height of 4 is 1. The height of 2 is 2. The height of 8 is 1. And the height of 5 is 3. If we look at the balance of all of them, we see that 1 is balanced. 3 is balanced. 4 is left heavy because the left is 1 greater than the right, but it's still okay. It still maintains the AVL property. If we look at 2, we see that it is right heavy because the right-hand child has the bigger height, but it only differs by 1, so we're still okay. 7 is balanced. 8 is left heavy. And 5 is going to be left heavy as well. But in all of these cases, the difference is always 1, 0, or minus 1. So the AVL property holds and we're fine. So now let's say insert the number 6. So we go to the root. We say, do we go left or right? Right. We're at 8. We're inserting 6. Do we go left or right? We go left. We're now at 7. We're inserting 6. Do we go left or right? We go left. And we've now found an open space. So in this case, we can now insert our new node 6. to the left. And now we said, well, by inserting the node 6 over here, we've potentially broken the balance on 7, 8, and 5, because we can only have broken the balance on the way up to the root. Okay? There's no way that inserting a 6 over here would break the balance over here at 2, or at 4, or at 1 or 3. Okay? So let's have a look at that path and see if we have broken the balance. So, first thing we do is we say the height of 6 is going to be 0. The height of 7 is going to be 1. The height of 8 is going to be 2. We can then say, well, 6, the left child is -1, the right child has height -1. So that one's balanced. On 7, the left child has height 0, the right child has height -1. So that one is going to be left heavy. But the difference is still less than or equal to 1, and so we're okay. When we look at 8, we say, okay, the left child has a height of 1, the right child has a height of -1, and 1 minus -1 is equal to 2. So we've broken our AVL condition. And so we have a problem at the node containing number 8. So we need to see, can we perform a rotation to fix this? And so we see that our problem node, number 8, is double left heavy, right? The difference is 2, and it's heavy to the left. We can look at its left child then, and we see that that one is also left heavy. And so in the case where all the arrows are pointing left, then we can use that previous rotation. So we can say, do a right rotation on 8. And so we say, as we did before, we see that we have 8 and 7, 8 and 7, and we need to do the rotation so that 7 becomes the root. So we say the rest of the tree will stay exactly the same as it was before. Sorry, that was... But now we're saying that the root over here, the root of that subtree is now 7. And that 8 must go to the right. And from there, we then need to fill in all the missing nodes. So, what goes to the right of 8? Well, there was nothing there to start with, so we don't need to worry. What do we have that was less than 8 and bigger than 7? Well, there's nothing there, so we don't need to worry about it. What do we have that was less than 7? Well, we had 6. So in this case, it goes to the left of 7, 6 over there. All the balances and everything on this side have stayed the same, so we don't need to worry about those. Let's see if we fix things on this side. So to the left of 7, we have 6. Its height is now 0. 8 has a height of 0, which means that 7 has a height of 1, and 5 has a height of 2. These were all the same as they were before. Sorry, 5 has a height of 3. So we now look at the balance. So we see that 6 is balanced because its left child has a height -1, its right child has a height -1. So we say 6 is balanced. 8, its left child has a height -1, its right child has a height -1. So that's also balanced. We see 7, its left child has a height 0, its right child has height 0. So that's also balanced. Then 5, we see its left child has a height 2, its right child has a height 1, which means that it is left heavy, but the difference is 1. So we're okay. So the AVL property now holds, and we see that we fixed it using that single right rotation. So the AVL property holds. So suppose we have this tree now, and we want to do an insertion of 5. So we can say, well, does 5 go to the left or right? It goes left. Does it go left or right? It goes right. We're now at 4. Do we go left or right? We go right. So we insert 5 over there. Okay, now let's check our AVL property. So I should have mentioned this before. This entire tree beforehand was indeed an AVL tree. But now that we've inserted the value 5, we now need to double check our heights from 5 all the way up to the root. So we see the height of 5 is going to be 0, the height of 4 is going to be 1, the height of 2 is going to be 2. The left child of 5 has height minus 1. The right child of 5 has height minus 1, which means that this one is balanced. If we look at 4, the left child has height minus 1. The right child has height 0, which means that it is right heavy. But the difference is only 1, so we don't need to panic. If we're at node number 2, we see that the left child has height minus 1. The right child has height 1. So minus 1 is equal to 2. And so at this point, the AVL property is broken, and we see that it is double right heavy. Okay, so we have a problem at 2. It is double right heavy, so we look at its right child. That child is also right heavy. Okay, so once again, we can fix this with a single rotation. And so it's just the opposite of what we did earlier. So now we do a left rotation on 2. So the rest of our tree will stay the same. We'll have 6, 8, and 7 as before. And then on the left-hand side of our tree, okay, we now see that 4 should come up to the root. And so 4 is the root, and 2 goes to the left. And now we insert all the other nodes that are left. So if there's anything to the left-hand side of 2, it is then less than 4. It is also less than 2, and so it would go over here. But because there was nothing there, then we don't need to worry. Okay. We can then say, was there anything to the left of 4? So it was bigger than 2, but less than 4. That would be less than 4, but bigger than 2, and it would go over here. So there was nothing there in that case, and so we don't need to worry. And then down here, we see that there was 5, and 5 was bigger than 2 and bigger than 4, and so it should go to the right-hand side of 4. And we see that that tree is now balanced. If we go in, we can see that the height of 2 is 0, the height of 5 is 0, the height of 4 is 1. And so if we look at the balance, both children on 2 are minus 1, so it's balanced. Both children on 5 are minus 1, so it's balanced. Both children on 4 have height 0, so that's also balanced. The heights on the right-hand side are exactly the same as earlier, so 0 and 1. 7 was balanced, 8 was left heavy, but only singly. So that was fine. If we look at number 6, we can now say both children have height 1, and so in that case we're going to say that it's balanced. So the AVL property holds all the way through this tree, and so this is an AVL tree. Okay, so let's do another example. Back to the original tree that we had before. We are happy that this is an AVL tree, everything is balanced. And now we're going to insert the number 3. So we say, do we go left or right from 6? Well, 3 is less than 6, so we go left. Do we go left or right from 2? We go right. Do we go left or right from 4? Well, we go left. So we now insert the number 3. Okay. From here, we now need to go through and check our AVL property, and we would need to check it from 3 all the way up, back up to the root, and make sure that we haven't broken anything. So we can see that the height of 3 will be 0, the height of 4 will be 1, the height of 2 will be 2. Let's look at the balance. So both the three subtrees are -1, have height -1, and so that's balanced. 4, well, the right tree has 0, the left tree has 0, the right tree has -1. So that is going to be left heavy, but the difference is only 1, so we're still okay. If we look at number 2, the left subtree has a height of -1, the right subtree has a height of 1. 1 minus -1 is equal to 2, which means that there is a problem. Okay, and so we're going to say that the problem is to the right, and so this is double right heavy. There is a difference of 2, and it's to the right. Now this time if we look at it, we see that the problem is at 2, it's double right heavy, and its right child is left heavy. So let's try and do the same thing that we did earlier in order to solve the problem, and let's see if it works. So beforehand, we did a left rotation on 2, so let's try and do the same thing. So we take its right child, and we bring that up as the root, and so we would end up saying, okay, 4 is going to be the root of that subtree. We then say, where does number 2 go? Well, 2 would have to go to the left. And if we look at number 3, we say, well, where can that be inserted? Well, it's less than 4, and it's greater than 2. But we see that just as we had a zigzag shape there, we've got the same zigzag shape here. And if we look at the balance, we'll see that this has height 0 and is balanced. 2 has height 1 and is right heavy. And 4 has height 2, but is now double left heavy, because it's got a height 1 on that side and a height -1 on this side, and so the AVL property still doesn't hold. So we see that in our previous examples, we always had the problem nodes in a straight line, either going to the right or going to the left. But when we have the zigzag shape, we unfortunately need to do 2 rotations in order to fix the problem. So the first thing we do is we take the zigzag and we see if we can turn it into the straight line. And so we do that by looking at the bottom section first, that section over there. So let's have a look. What we can do is we can now do a right rotation on 4. And that says, take the left child and bring that up. So we're doing the rotation on 4, so 2 stays exactly where it is. We're bringing 3 up, so that takes 4's place, and 4 is bigger than 3, so it goes to the right. And we see that we've now turned it into the straight line problem that we had before, and we know exactly how to solve the straight line problem. And so we can then say, well, in this case, we do a left rotation on 2, which then says we take its right child and bring it up. So 3 is now the root, 2 goes to the left, and 4 goes to the right. And we can see that that gives us a nice balanced tree. And when we insert it back into our original tree, like that, we can now calculate the balance everywhere. And we see that 2 is balanced because both its children have height -1. 4 is balanced because both its children have height -1. 3 is balanced because both its children have height 0. I'm afraid 0. 7 is balanced. 8 is left heavy, but the difference is only 1. The left side has height 0. The right side has height -1. So we're fine. When we're at 6, we then say, okay, so the height of 8 is also going to be 1. When we're at 6, we say, look at the left and right children, and we see that they're both 1, and so 6 is completely balanced. And so the AVL property holds everywhere, and so this is still an AVL tree. So we see that there are now 2 cases. We have the case where we have all three problem nodes in some kind of straight line, either going left or going right, or we have some kind of zigzag going right and then left, or left and then right. In the straight line case, we can do one rotation, and we are guaranteed that the problem will be fixed. In the zigzag case, we have to do two rotations, one to turn it into the straight line, and then one more in order to actually fix the problem. Okay, so let's formalize the idea of our double rotations again. So just like we had with the single one, we have some node X, some node Y. Y has some left subtree and some right subtree, and X has some right subtree, A, B, and C. In the previous case, where we could fix things with a single rotation, we said that the problem was at X and that it was left and left again. In this case, we're saying the problem is at X and we have to go left and then right. All right. So we're going to say that the height of B is going to be H, which means the height of A is going to be H or H minus 1, because they differ by at most 1. That means that the height of Y is equal to H plus 1, and the height of C is going to be either H or H minus 1. If it's H, then we don't have a problem and the AVL condition holds. So we're not really interested in that case. But if it has height H minus 1, then we definitely have a problem, because then the difference between the two is going to be 2, and we're going to find that X is going to be double left heavy, but Y is right heavy. And so we have the zigzag shape again. So in that case, we need to do the double rotation. So we first need to rotate up so that the top of B moves up to where Y is, and Y moves down to the left. And then once that's in a straight line, we can then do the full rotation, and we'll see that that fixes everything. So let's do some more examples. Let's say we have a tree of 5, 2, and 1, 4, and 3, 8, and 6. And now we want to say, first thing, is this an AVL tree? Well, let's fill in the heights. So we've got 0, 0, 0. That will be 1. This height will be 2. This height will be 1. And this height will be 3. All these leaves are balanced, so we don't need to worry about them. We can see that 4 is left heavy, but the difference is only 1. It's 0 and minus 1. So 0 minus minus 1 is simply 1. So we don't need to worry about that. Same thing at 8. We're going to see that it's left heavy, but the difference once again is only by 1. 0 and minus 1. If we look at 2, we see that the height is 0 and 1, and so the difference between them is 1. So we're still okay, although we are right heavy. And up at at 8, we said that was balanced. At 5, we've then got a height of 2 on the one side, a height of 1 on the other, so it is going to be left heavy, but the AVL property holds because the difference is only 1. Now at this point, if I say insert the number 7, well, we say it goes to the right of 5, to the left of 8, and to the right of 6. So we insert it over there. We then say we've potentially broken everything all the way up to the root. So we say, let's have a look at the balance conditions of all of them. So the height of 7 is going to be 0, and it's balanced. The height of 6 is now going to become 1, and it's going to be right heavy. But the difference between 6's left child and right child is only 1, so we're okay. We go up to 8, we see that its left child has a height of 1, and its right child has a height of -1, which means that there is a problem, because 1 minus -1 is 2. So we say that 8 is now double left heavy. So 8 is left heavy, and its left child is right heavy. So we have the zigzag pattern. So in this case, we need to do 2 rotations in order to fix this. The first thing we do is to make it into a straight line. So we see 8 stays exactly where it is, and we then do a left rotation on 6, which means that 7 gets pulled up, and 6 goes down to the left. So in this case, we've now got the straight line, and we know then that we can fix the straight line by doing a right rotation around 8. So here we did a left rotation around 6, we now do a right rotation around 8. And so that will take us, so 8 goes down to the right, 7 gets pulled up as the root, and 6 is still less than 7. So that's what the new tree looks like. So if we can do all those changes by just changing pointers. So we can do that in constant time. 7, 6, and 8. We say the height of 6 is 0, the height of 8 is 0, and the height of 7 is now 1. 6 is balanced, 8 is balanced, as is 7. And 5, if we look, its one child has 2, its other child has 1, and so the difference between them is just 1, and so we are happy that the AVL property holds. So this is now once again an AVL tree. So our algorithm then for insertion is going to look something like this. We find the problem node. If the problem node is P, then we say if P is double left heavy, then we must look at its left child. So then we say if the left child of P is left heavy, then in that case we have the straight line. So we've said we have P, which is double left heavy, and its left child is also left heavy. We have the straight line, and so in this case we do a right rotation of P. Otherwise, if the left child of P is right heavy, then we have this case where P is still left heavy, but its left child is right heavy. So we now have the zigzag case, and in that case we need to do a left rotation on P dot left, and that gets us to the straight line. And once we've got the straight line, we can then do a right rotation of P. And that will handle the case when P is left heavy. The other cases are just symmetrical. So the other cases say if P is double right heavy, then we look at its right child. And we see if it's right heavy. And if it is, then we have the straight line case once again. And so in that case, we then do a left rotation on P. Otherwise, if we have the other case where P dot right is left heavy, then we have something like this. And so the first thing we need to do is rotate right on P dot right. In the same way up here we rotated left on left. Here we rotate right on right, and then that will get us to that case, and the way to fix that case is to just go a left rotation on P. And we are guaranteed that we will then be able to fix the tree in 1 or 2 rotations. Now the other operation that we spoke about was deletion. So if we want to remove an item from the tree. So suppose that we have the following tree. So this is the same tree that we had earlier, and so we can say it is an AVL tree, we know that. And if we want to delete the number 3. So we already have an algorithm to delete a number from a binary search tree. And so in this case, we search through and we find the value 3. We see, does it have any children? So no, it doesn't. So in this case, it's a leaf, and we can simply delete it. Right. Now that we've deleted it, we've potentially messed up the path all the way from its parent back up to the root. So we now need to just double check. Well, in this case, 4 is balanced, 1 is balanced. Both of these have height 0, so 2 is balanced. 7 is balanced. 8 is left heavy, but the difference is only 1, so we're okay. And with 5, maybe let me fill in the heights for us. So 0, 0, 0, 1 and 1. So both children of 5 have height 1, and so 5 is balanced, and so this is an AVL tree, and we're happy. So if we follow the path all the way up to the root, and we see that we haven't broken anything, then we're happy it is an AVL tree, and we don't need to worry. Alright, so suppose we have this tree. Let's double check that it is indeed an AVL tree. So I'm going to fill in all of our null pointers. And we know that all of those heights are going to be -1. We then can fill in the heights of all the nodes going from the leaves back up to the top. So we see that 48 has height 0, 62 has height 0, 88 has height 0, 50 has height 1, 32 has height 0, height 1, height 2, height 3. Let's double check the balance. So 48 is balanced, 62 is balanced, 50 is balanced. 88 is balanced. 78 is left heavy, but it only differs by 1, so we're okay. 32 is balanced. 17 is right heavy, but it only differs by 1, so we're okay. 44 is right heavy, but again it only differs by 1. So our AVL property holds throughout the tree, and so we know that it is an AVL tree. Now, I say let's delete number 32. So we go in, we follow our normal algorithm for deletion. We say 32 is less than 44, it's greater than 17, and we found the node. We look and see, does it have any children? No, it doesn't. So in this case, it's an easy one to delete, and we simply delete that item. Now that it's deleted, we need to double check that the path all the way from the deleted node up to the root, we need to double check whether we've broken anything. So this is now -1. So -1 and -1 means that this is now, that's number 17 is now balanced, and it has a height of 0. If we go up to 44, we see, okay, well the left child is 0, the right child is 2, so there is a difference of 2, and it is double right heavy. Double right heavy, we look at its right child and see that it is left heavy. So we go right, left. So we have the zigzag, which means that we expect to have to do 2 rotations in order to fix this. So our algorithm says, let me just shrink it and move it to the side. Our algorithm says, do a right rotation on the child first. So the right rotation means that 78 moves to the right and its left child moves up. So we're going to have a right rotation on 78, and that's going to leave us with a tree that looks like this. The rest all stays the same. 78 moves to the right, and 50 moves up here. We then look at all the other children and we say, where do they all fit in? So the left child of 50 stays the left child of 50. The right child of 78 stays the right child of 78. And then the right child of 50 has to move somewhere else because now 78 is there. So we say, well, it was greater than 50, so it must go right, but it's less than 78, so it must go left. So the right child of 50 becomes the left child of 78. So that's the first rotation that we've done, and we will see now that we have a double right heavy, and its right child is now a right heavy. So we know how to fix that. We now do a left rotation on 44. So a left rotation on 44. And that says that 44 moves to the left and its right child moves up to the root. So 50 is now the root. 44 has moved down to the left. The left child of 44 stays exactly where it was. Sorry, 17. The right child of 50 stays exactly where it was. So that would be 78, and all of 78's children stay exactly where they were. Oh, sorry, that shouldn't have been 78, that should have been 62. So that's there. So the left of 44 is fine, the right of 50 is fine, and we just look at the left child of 50. Okay, we can't leave it where it was because 44 is now there, so it now becomes the right child of 44. And we can see that not only is this a balanced tree, but it's worked out to be a perfect tree as well. So everything is now balanced. Everything is balanced, and this is an AVL tree. This works exactly the same for the other cases. So if 32 happened to have one child, then you would delete it and set the parent to point to that child. And then after that, you would check whether the balance has been broken, and potentially then you have to do rotations from where the node was removed all the way back up to the root. When inserting, we guaranteed that we only had to do a maximum of 1 or 2 rotations in order to fix it. For deletion, you unfortunately need to check all the way back up to the root, because you could possibly have to do a couple more rotations along that path. So the final thing about AVL trees that we need to prove, that we need to know about, is this proof that says that an AVL tree will always have logarithmic height. So the way to do this is to say that we know the minimum number of nodes that must be in an AVL tree of some specific height. So I can say that the minimum number of nodes is going to be the current node plus the minimum number of nodes in the left subtree and the minimum number of nodes in the right subtree. So let's say that n is, let's say nh is the minimum number of nodes in an AVL tree of height h. And then we can say, well, the minimum number of nodes in a tree of height h is going to be the minimum number of nodes in the left, which will have to be h minus 1, plus the minimum number of nodes in the right, which will have to be h minus 1, plus the current node. So it's going to be that. The problem is that this isn't actually the minimum, because we allow these two heights to differ by at most 1. So if this one is h minus 1, then this one is allowed to be h minus 2. And so actually the minimum number should be h minus 1 and h minus 2. Similarly, this could be h minus 2 and that could be h minus 1. But either way, this function works out to look like this. It's the minimum number of nodes in the one tree plus the minimum number of nodes in the smaller of the two trees plus the current node. So we see that this has given us it's called a difference equation, some kind of recursive formula. And we can see then that we could also write n h minus 1 as n h minus 2 plus n h minus 3 plus 1. So all I've done is shift h along by 1. And we could continue writing it out like that. But if we substitute the second equation back into the first one, we see that that gives us that nh is equal to n of h minus 2 plus n of h minus 3 plus 1, which is this term, plus n of h minus 2, which is this term, plus the 1. So if we rearrange those things all a bit, we see that we get 2n h minus 2 plus n of h minus 3 plus 2. So we know then that NH must be greater than 2NH minus 2. We can get this relation because we know that this over here is going to be positive. We know that that over there is greater than 0. Greater than 0. And so we're saying some number plus some other number. So if we get rid of that, we know that NH is going to be greater than that. It's bounded below by that. Now what we can do is we can say, well, if we know this, we also know that NH minus 2 is going to be bigger than 2NH minus 2 again, so minus 4. And so we can substitute this back into that original equation, and we see that NH is greater than 2 times this line. So 2n of h minus 4. Like that. And so that gives us that n of h is greater than 4n of h minus 4. We can then substitute that in again. And so we can say, okay, well, we know that that n of h minus 4 is going to be greater than 2n of h minus 6. And so if we substitute that in, we end up getting that nh is greater than 4 times 2n of h minus 6, which gives us 8n h minus 6. So on each of these lines, what we can see is that we're saying that n of h is greater than 2 to the power of some number, I, and n of h minus 2i. So the question then becomes is how many times can we subtract 2i from h? Well, let's have a look. So we're going to say, apologies, I left out one thing at the beginning. I left out the base cases. So the base cases must say, well, n of 0, the minimum number of nodes we need for an AVL tree of height 0 must be 1, where we just have the root. And we can also say that n of 1, where we have height 1, we know that we must have at least 2 items to get height 1. So this gives us our base cases. We know those answers. So down here we can say, well, if we have height 0, we know the answer is 1. If we have height 1, we know the answer is 2. If we have height 2, well, we can subtract 2 only once, and then we get back to there. So in this case, we can subtract 2 once. If we have height 3, how many times can we subtract 2? Well, we can subtract it once, and then we get back to one of our base cases. If we have height 4, how many times can we subtract 2? Well, we subtract it once, and once again. So twice. For 5, we can subtract it once, which gets us to 3, and once again, which gets us to 1. So that's also twice. And we'll see that it goes 6, 7, 8, 9, and as that grows, the number of times we can subtract it is always that number divided by 2, in integer division. So if we take the floor of that division. So what this says is that we can keep doing this until we can do this h over 2 times. So it says that we can do this, I goes from 1, 2, 3, 4, 5, 6, 7, all the way up to h over 2. So I could continue doing this step over here, where I replace it and then try again, and replace it and try again, and replace it and try again. And it would take me h over 2 times until I get to either n0 or to n1. And so I know that n, the minimum number of nodes, is greater than or equal to 2 to the h over 2 times by some constant. So, and that constant will either be times by 1 or times by 2, depending on whether we get back to 0 or to 1. But nevertheless, if it's times by 1, then this holds. And if it's times by 2, then it certainly is bigger than this. So we can just leave it at this, and we can say that n is greater than or equal to h over 2. So if we know that the number of nodes in a tree, the minimum number of nodes in a tree of height h is at least 2 to the h over 2, well, we can take the log of both sides. So we get log n on the left, and that's greater than log of 2 to the h over 2. And using our log rules, we can say, well, h goes down there with a 2, just like that. And log base 2 of 2 is simply going to be 1. And so we end up with this inequality. We can multiply both sides by 2. And so we get an upper bound on h. We know that h must be less than 2 log n. And so we can never have a height that's bigger than this if there are n numbers in the tree. All right. And so if we've said that h is bounded above, if we think back to our definition of big O, that's exactly what big O meant. It's bounded above by some shape of function. So we can say then that h is order log n. And so we know that if we're talking about an AVL tree, that the height of the tree will always be less than or equal to 2 log n. And in fact, if you do some very clever maths, then we can get that bound even smaller to about 1.44 plus some constant. Okay, so I hope that gives you an idea of how AVL trees work. Certainly practice with all of those. These are a good way to get marks in your tests. Okay.